see if this is working. OK, great. Let's start. So last time we talked about so as I mentioned last time, if I had my way, I would actually have liked to have reached this point in the course about 4 weeks earlier, because I think this we're talking about now is very, very relevant for deep learning today and tomorrow and the day after. But we needed the background to sort of have the basics, but I wish we could have gone through it even faster. So recall the story is that we have these models, transformer-based, but just like stepping back a bit, which are pre-trained on lots and lots of data. Okay, so we have pre-trained model. Right? Typically, today, trained by self-supervision, quote, self-supervision, using lots of data. And we think of this as being a kind of glorified PCA. That's the way we've been thinking about it so far. And we want to use it for a particular task. As a component / building block a task of interest. So we talked about two approaches already for dealing with this. I'm going to kind of think about them kind of the abstract level. And then we're going to talk about some more different things that can happen. So classic approach. I'll give this a name. So this has lots of names. So the name often is called as linear probing. Says treat pre-trained model as a feature extractor. So what do you do? So you have given task-specific data, training data, okay? So we just have a set of xi, y pairs. So this is supervised learning. Given task-specific training data, construct something that looks like this. Xi goes in. Now this could be a whole sequence. This could be. I'm abstracting all of that away. And what you do is you extract features from here. So you send probes in. Think of it as like little wires that you're sending into here. Okay. So these are probes that you put into the pre-trained model, which are looking at, for example, activations. They're looking at activations in different places. Typically, standard approach, just think of the activations as coming off the penultimate layer. Okay? But you could put them anywhere you want. And then you have a task-specific head. And then you have your loss. So you construct this thing. So this thing has this thing as a feature extractor. So X is some complicated thing. You pull out some set of activations. You hope that if this thing is functioning kind of spiritually like a glorified PCA, that somehow this stuff has been appropriately dimensionally reduced or aligned or purified, so that hopefully your task-specific head can learn what it needs to learn given the amount of data that you have in the supervision. Okay? So then what you do is you just train the head. You freeze this. Meaning all the weights inside this are not changing, and you just train this. This is, again, that we reviewed before. It's the classic PCA for dimensionality reduction, followed by some learning method on the dimensionality reduced data. So this, hopefully, is very clear to everybody. You can do this. There's many choices here, so I want to make sure. You can have choice of what you actually pull out as your features. So we talked about, for example, in the context of BERT, where this was studied extensively, people said, well, you can use BERT, and you can pull out the top penultimate layer features, the layer before that, the average of them, and so on. All of that is a design choice going on here. How do you make these design choices? The same way you do any other kind of hyperparameter search, some validation approach. So this is the basic approach. Okay, so we have this. So then we talked about another one, which is called full fine-tuning. So here, you treat the pre-trained model as a building block with a good initialization. Okay, I should not do it right this way. The good initialization. So in this approach, what do you do? So I'm going to describe the current best understanding of what you do. Basically, since you're treating it like a building block with a good initialization, you're not wedded to the initialization. Whatever weights the parameters, whatever the weights happen to be at starting point is not necessarily where you're going to expect them to end up. It's just a starting point. So basic idea. Is train everything together. But I want to expand on this, right, practically. What do we do? You should actually, and this is I think I mentioned at the very end of last lecture. If you train everything together, right, you still have to introduce a task-specific head. Because the pre-training objective is presumably nothing like your objective, the task you want to do. So when you initialize, or might not even be the same type, right? Could be even like the wrong number of outputs. So in this case, you have to introduce this, which means you have to initialize that somehow. But the question becomes, how do you initialize this? Right? How to, quote, initialize. Task-specific head. So one thing you can do is approach 0. Random initialization. Which is, of course, what you always do, right? If you don't know what to do, randomly initialize it. So you can randomly initialize it, and great, it's randomly initialized. And then you just start doing your fine-tuning. Okay, so we mentioned this last time at the end. So if you did that, though, the problem is, at the very beginning, the task-specific head is really not aligned to the task at all. And so when it uses the gradient update for it is somewhat reasonable for the weights inside here. But when you do backprop and you send gradients back, those are you can think of them as either very noisy or just completely out of touch with what you're trying to do. And so what you're going to do, if you do that, is oftentimes you will cause the pre-trained model, which is now no longer frozen, to get perturbed in some way. Right? Now this is perturbed in some way, and then this task-specific head eventually will get reasonably good at the task, if there's any hope at all. But now it's dealing with a randomly shaken pre-trained model that might have lost some of the good qualities it had before. Is that clear to everybody? So the approach 1 is random init followed by task head only training. Freezing pre-trained model. Okay? And then this is your initialization. So what this does is this initializes the task-specific head to something which is sort of reasonable for this task. And then you, after you do this initialization, then you fine-tune everything. So now you allow gradients to pass through and adjust everything. Okay? So these two approaches are hopefully clear to everybody as something you can do. So now, what is there's many, many ways of thinking about the trade-offs between them. But let's just try to understand some of the basic trade-offs. The classic approach has fewer parameters that you have to tune, right? Namely, just the ones in this task-specific head. So oftentimes, this approach works much, much faster. We have fewer things to update. And will sometimes fit in memory at times when this will not fit in memory, the second approach. You might not have enough on your machine to be able to actually train all this. So in those cases, of course, if you cannot do this at all, you feel like you're just stuck doing this. People have found for many tasks, the performance advantage of doing full fine-tuning is quite substantial, right? It's like, in many tasks where you measure accuracy in percentages, it's going to be like tens of % better than this. So it's quite a big advantage to be able to do this. So now, where do you go from here? Okay, there's many different avenues. We're going to talk about some of them, but the literature here is continuously expanding. So one thing that you can do is to say, take this seriously, right? That this is the approach of what you're going to be doing. And it says, well, if you want to do better, way you can do better is to get better pre-trained models. So let's say approach A. So how can you get better pre-trained models? So this is make them bigger, use more data. these are the obvious choices. Okay? There's a few other important things here that I want to mention. Instead of just making them bigger and using more data, you can also use better data. So if you have a way of telling that you have data of different levels of quality, maybe you want to use data that's higher quality. Okay. Quality of data can be on many different axes. Generically, you should think of it as less noisy and a better exemplars of the pattern you're trying to see, and all the variation thereof. But another thing you can do is use more proxy tasks for self-supervision. Right? See if you can, like the idea is especially for this approach, that to the extent that there's some degree of alignment between what it is that the new task you want to learn and what it is that this thing was pre-trained on, you expect intuitively for you to get better performance. Right? So if you can have a diversity of proxy tasks that are more likely to cover the kinds of things that you're expecting to do in terms of learning the underlying regularities in the data, then that can help. Okay? So this is one line that one can follow. There's one more that I want to get to later, which is I want to talk about this meta-learning. So I want to mention that here. It's kind of, you can think of that as being sort of in this line. So the idea is, when I think of it as meta-learning, is you think of your model as the point of the model is to be able to adapt to new tasks. Right? The point of the model isn't to just do itself. Like all the pre-training, everything you're doing is just so you get something which you can then adapt to a new task. So take that seriously and ask, well, what will make me allowed to adapt to a new task? So I'll talk about this at the end. So, but I want to acknowledge that there is another way, another dimension to all of this. The other dimension to all of this is to ask, suppose, think of it this way. Suppose you said you have enough compute budget and memory in your GPU and everything so that you can do the classic approach. But you don't have enough to do full fine-tuning. Everyone see? Like, you have resources to spare here, and here you don't have enough. So can you do something in between? Okay, so this is thinking of it from the perspective of computation and what you can implement, not changing the pre-trained model in any way. Okay? So for this, you have to say, okay, why is there any hope of doing something in between full fine-tuning and classic? Because, what are you treat this pre-trained model as just a bunch of weights. What are you going to do? So does anyone want to give, based on stuff that we have learned, why is there any hope that you could maybe do something in between full fine-tuning and classic? So think about, again, orders of magnitude. Think of the pre-trained model as having potentially, hundreds of millions of weights associated with it. Okay? So, or billions of weights associated with it. So now I'll turn it over. Why is there any hope that you can try to do something here and have it succeed? Yeah?
Maybe like the analogy of like gradient descent and stochastic gradient descent, where instead of just one data point, you can maybe do a sample of weights that you're updating.
Ah, okay, great. Okay, so I'll actually call that out. That wasn't what I was thinking, but that's an interesting perspective. So I'll say one idea, right, is to say maybe we can update just a subset, a strict subset of weights in the pre-trained model. Okay? And now, in here, we can have different categories. Let me break this down into subcategories. Right? That's what you were saying, right? So we can, if everything doesn't fit, maybe we can just tune some of them. So again, let's think about it. What do you need, right? Like, where is the bottleneck in terms of your memory and so on in your compute? Okay, let's think about that for a minute. So you have to be able to store the thing that you're updating and changing. And you also have to be able to successfully get gradients to that point. Right? So if you think about backprop, for running backprop to get gradients, you have to store activations, right? Or activation-like things to be able to get the gradients down to where you are. So there might be some technical, so everyone see this? I want to make sure I acknowledge it right here. So if you want to use a subset of weights, you do have to be a little bit careful of how much is going to be the memory or compute footprint of actually being able to adjust those weights. Because at the very basic level, you have to be able to get gradients to them. Okay? But let's just put that hold that aside. So I'll maybe put that as a note. Note must be able to compute gradients to these weights. Okay? So now in here, there's a few choices. The one you mentioned, right, is update a different set of weights. Oops. Right, as you go. So that idea, right, of just updating a different set of weights as you go, this should remind you of something that you have learned about in your optimization class, I believe, called coordinate descent. Right? This is taking a coordinate descent approach to the problem. So if you take the coordinate descent approach, I think details matter, right? So if you do a coordinate descent style approach to this, you do still have to keep all the coordinates around that you're going to be updating. Right? So it can potentially buy you something to do it this way, but this tends to be more of the style of, okay, I want to do full fine-tuning, but I can't possibly even execute one step of SGD in my hardware as it stands. So I have to do tricks to get my hardware to basically be able to do pieces of it at a time. Right? So that's more this style. But it's good to remember it. So I want to talk about what's a different approach where you might only want to update a subset of weights that one can do. Yeah? Okay, so you can follow a version of this, because that's what you're saying. So again, I'm going to, okay, so just to repeat what you said. What you said was that maybe what we can do is to follow the strategy that we did here in approach 1 of initializing the task-specific head and say that you've initialized the task-specific head based on freezing the entire pre-trained model. Maybe we can repeat this selective unfreezing through the pre-trained model itself. Did I get that right? Okay. So, yeah, okay. I'll make a note of that. Wasn't what I was thinking. That's fine. Okay, so if you do this, again, there's still the question. At the end of doing this process, you have to decide when you're going to stop unfreezing. So this could be, I'll say one way you can do it is to say you just pick a few layers at the top and you train all of them, if you can't fit everything in memory. Okay? Just fine tune. Top K layers. You can also you can be much more general than this. And in fact, in ConvNets and for images, there's a paper that came out last year in which they showed that actually, depending on the nature of the problem, the best thing to do might actually be to freeze everything except the bottom layer. Because the bottom few layers. Because the bottom few layers are the ones that are seeing the data. And if the data here is slightly different than the data you were pre-trained on, what you have to do is actually adjust the feature extraction at the very basic level. Just tune that a little bit to get that to properly align to what you're seeing. And then all the higher level processing can stay exactly frozen where it is. Right? So this is like a general, not from the top down, but just more generally, selectively unfreeze based on nature of task. So in particular, if it's the data has really shifted, the covariates, the inputs, have really shifted their distribution in some interesting way, then maybe you want to target something closer to the covariates. If it's really more, the input distribution is very much like what you saw before, then top layers only. Okay, so these are all kind of in this subset of weights category. I'll put one more version of this, which is interesting. Yeah. Good. So yeah, I'll comment that as category 2. So I'll come right back to this, right? So just hold on a minute. I want to finish filling out here. So one more comment that something you can do is that, for example, if your model is a transformer-based model, right? You actually have different kinds of components inside. You have these multi-layer perceptron type components, and you have query key value components that are doing attention stuff, right? And so what you can also do is you can selectively unfreeze just the attention parts and say maybe what's different in this problem is actually the context dependence is the main thing that's different. And many problems, this also works. Yeah.
I guess I just want to clarify what you mean by like it won't fit into memory. So if we have frozen layers, it doesn't like contribute to the memory because there's no gradients associated to those parameters, and thus like that itself is not like adding to the memory, or like we still need to keep those layers somewhere, right? Some reference.
Yeah, great questions. The question was, when we talk about like freezing something, what does that actually buy us in terms of memory? Right, that's what you're asking, right? Because you still have to run the model, which means you do have to access all of that stuff. And you need those weights somewhere so that you can access them, so you can do the compute, right? Great question. So the most basic way to think about it is, if you're going to do, so think about, for example, you want to use Atom to do the optimization. Okay? So in Atom, what do you have to store? Anyone? Let's review. What do you need to, what is the memory footprint of Atom, if using Atom as the optimizer? Yeah?
So you have to store a gradient and like the square of each element. So since it's second order.
Yeah, what you have to do is you have to store both the momentum terms, which is like the average gradients so far, and for every weight you might want to update, and you have to store something you're using to square the squares, so you have to keep track of the size of those particular parameters, so you can make an adaptive step size, right? This is something you have to store that's different from the particular gradient you're going to compute from backprop in this SGD step. Okay? So you see how something you're going to update using Atom, you're definitely going to pay, 3x in terms of, but you have to store these things. Even if you think about the SGD stuff as being potentially you can burn them, here you just store the stuff around. So that's an example, right? There's also the tricky business of being able to get the gradients running backprop. So if you were only running the model, so for example, this model was truly massive, right? Really, really huge, and you had very low compute of what you can do. So low that you couldn't even load the entire model into your memory to run it. Okay? Suppose you're in that regime. You could still do this, right? You could do this by saying, maybe you could load one layer at a time. So you load one layer, you compute. Then you say, that's your new input. Then you load the next layer, right? CPU to GPU call, right? Right? Then you run that layer, right? Then you throw away everything. So you keep taking the activations and moving them up, 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 up. So everyone see this is something you could do, right? It would be slower, but the model is huge. There's that many computes you have to do. You only have, your GPU can do this much. You got to do it. Now you have here. Now, this thing you can train, right? Because you get gradients here. Thing is, though, if you keep running through this thing going only upward, you're throwing away a bunch of activations, which means you're also throwing away the ability to compute the gradients on a backprop pass. Right? There's tricky, interesting ways of kind of being able to do this to get backprop to work. But based on stuff we've been taught you so far, you've lost something in doing this. So yeah, it really does depend on the implementations here a lot to think about what's going on. Okay, great. So now we've talked about these different ways of doing things between fine-tuning and the classic approach of training everything, of just training the head. So you can unfreeze selective parts. Good. But I want to get to the comment that was raised, which is that maybe you can somehow pool stuff across the different weights. Like maybe all these weights don't have to update in their own independent way, right? That's the key idea. So first, let's think about, based on stuff we've known, so don't independently update each weight, okay? So let's think about, why is this reasonable. So I'm going to put one reasonable thing on the table to start with, which is, remember, this is deep learning. Maybe we can do this. We cannot do the other thing. The simple reason that we can do this makes it reasonable. Right? Remember that. OK, good. Let's put that aside for a moment and ask, intellectually, why would you believe it to be the case that maybe we shouldn't be independently updating each weight? Maybe we can still get benefits even if we don't independently update each weight. Why would you think that? Yeah.
It seems like for example, losing precision. So it's very similar to like quantization or like in the context of signal processing, like just reducing the number of bits of the precision of the update.
OK, actually, I'm going to put that aside as something, yet actually different. OK, so the comment was that this feels like it might be like reducing the precision, like the numerical precision. So going from floating points that are doubles to just floats, or maybe 16-bit floats, or maybe smaller, right? So that's actually a totally different, I'll put that aside as a different category, right? We can try to work with a quantized model. But you're right, there's a spiritual connection too, but I want to acknowledge that specifically as a separate thing. With a quantized model, so it'll fit in memory, okay? But, so the comment though was that maybe there is something here that's like quantization. So actually, that's true for those who know it. So I'm going to give a little brief aside to acknowledge the comment. So if you remember, if you've ever studied like compression, like JPEG compression or any compression approach, remember in compression, there's two different things that are happening. One thing that happens in lossy compression especially is that you actually transform the domain. There's some kind of transformation that happens. In JPEG, it's the DCT, the kind of Fourier transform that's done. And then you realize that in the transformed domain, most of the action is actually in a smaller set of smaller subspace. Then you use quantization appropriately to give appropriate precision to the places where there's action and nothing to places where there's no action. And that's how JPEG works. Right? So there is an intimate connection mentally between quantization and looking at things potentially in different domains. Okay, so you can do straight quantization, but you can also think about this looking in different domains. So one of the things that we've learned is that the way that these models work is at some point, remember, they're like glorified PCA. And we gave you an example in the midterm where we said, here's an example where you're just training something that's a square matrix. It could actually learn all degrees of freedom. Like, it doesn't matter. But given that we're using weight decay, we showed you that basically this thing will learn to actually favor certain directions. Okay? But that means, when you think about it, these models, whatever this model is, when you're doing full fine-tuning, what you're working with locally is the linearized version of this model around the neighborhood of the initialized weights. And so if this has billions of parameters, this is something which exists, again, in a billion-dimensional space. But it's probably not having uniform amounts of energy, of motion, along all those different directions. It probably has a non-trivial SVD. And it has some directions that are it's moving much more in, the same way that it is for JPEG. So what you can do is a category of things called low-rank updates. Which is, you say that you know that even if you were doing full fine-tuning, you'd probably only be moving in a subset of directions, dominantly. Does everyone see that? Because if these things generically... Okay, maybe I will step even further back. think about the size of your data here. Okay? If you're doing a task-specific thing with task-specific training data, maybe you have 1,000 examples. Maybe you have 10,000 examples. This thing has 10 billion parameters. Right? Remember, at the beginning of class, we said this kind of stuff happens. So this thing has fewer examples than it has parameters. You're not going to be able to move in all those directions anyway. You see that? Like, you just don't have enough data. So the only hope for success, the only reason there's any hope that you would ever learn the pattern is that the pattern has to be representable in some subset of directions. Because you can't possibly move in all of them independently, because you don't have enough data. Okay? That's the thing we talked about at the very beginning of the class. So that applies here. So given that you can only move, given your data, you can only move in a subset of directions, you hope that the updates you can do can just be low rank. And so you can simply think, so now the question becomes one of implementation. How is it that you can take the idea of doing a low rank update and realize it? So, because if I just say I want to, when you're doing full fine tuning, you're updating all these parameters. They will end up being approximately low rank updates anyway. But that's not good enough. You still have to track all that memory. So what can you do? So what this is done, the way this is done, I'm not going to go more into it. Again, if we had more time in the class, I would have like an entire lecture on low rank updates, but I wanted to make sure you got the idea. You can introduce factorizations. To your parameters, such that they will share lots of things together. Okay, so in general, if you have a matrix, you can write the matrix. So you have some matrix M that you want to, of weights that you want to adjust. You can think of it as starting initial condition plus some low rank update. So if this thing is big in terms of how many rows and columns it has, you can make this thing be small. For example, let's say choose only rank 3 or rank 4. So if this is a n, okay, I shouldn't use m. Turn everything upside down. W, okay. If this is an n by m matrix, W naught has n by m parameters in it, but here you can make this equal k times n plus m parameters. Right? Just think about the outer product form of the SVD. Okay, so I'm going to pause here to make sure haven't lost lots of people. We're talking here about how you can take something and make it think about low rank and translate a low rank update into a smaller number of parameters that you actually have to learn. Okay? So this is frozen. But if I think about outer products, so I think about W. Let's think about the SVD. Recall. Right? Everyone remember this? So these are vectors. So if this is n and this is m, this is an n-dimensional vector, and this is a m-dimensional vector. And how many terms are there in the sum? Well, it goes 1 min n m. So if you think about this from the SVD, this just tells you this is writing a matrix as a sum of rank 1 updates. where you start with the most important, then the next most important, next most important, next most important. If you're going to be moving along these weight matrices, you can just think of them also in terms of k rank 1 things added on. But that means these are the only parameters here that you have to compute gradients on. These guys. And you can do the updates on these. So this is low rank updates. It's the basic idea. There's lots and lots of variations here. So here I've described the most basic example, the low rank update example. But you can also, people have generalized this with the idea of what they call adapters, where you put some other small structure inside your pre-trained network that you tune that adapter. And you let everything else be frozen. You can think of this as a kind of adapter. Okay? So with this, I want to see, does everyone understand this general idea of you can do linear probing, treat the model as frozen, just generating features. We can do full fine-tuning, which is, in practice, going to be you look at the model and you look at all of its tangent features, all of these linearized, locally linearized features, and you learn from that model. And you can try to do something in between, okay, which is update a subset. Don't think about subsets. Think first subsets are just a particular way of having low rank. So think about some kind of low rank update structure. Or also then potentially work with quantization and really optimize everything. Okay. So lots of stuff one can do with basic kinds of the understanding you already have. Okay. With that, I wanted to change gears a little bit and to tell you about something interesting that happened, which you all know about, but we haven't talked about in the class, which is the idea of prompts. So, feels like it's totally different, but we'll soon connect it up to everything you just talked about. Okay, so maybe I'll just check. Has anyone here not heard the term prompt in the connection with GPT-style models? Okay, so there's at least one person here, so I will now talk about it. Okay, so the idea is, so remember we talked about, when we talked about word2vec, we said word2vec was trained to take words and embed them into some vector space, and we found the surprising ability of word2vec to actually do analogy problems, even though it wasn't trained to do analogy problems. Okay? So for GPT-style models, right? GPT-style models are basically, they're trained to do autocomplete. Right? They're just trained to predict the next token. That's all they're trained to do, right? That's the only task that they know how to do, is predict the next token. That's what they're trained to. Okay? So for this, people said, can I use a GPT-style model to solve some other problem? And I treat it like a black box. So they said, okay, maybe I can, let me see how would I use this to solve the problem of what's the capital of a country? Okay? So problem. Country capitals. So the question is, Here's a country. What's the capital? So people said, hey, let me see what happens if I use GPT on it as a black box. So you feed GPT, feed this model. The input, the capital of France is, as the input. And you see, what does it complete it with? Okay, the model returns Paris, period. Okay? Does everyone see what we're doing here? We're using an autocomplete, right, to solve a problem. And we solve the problem by asking the model to complete a sentence. Is that clear? Okay. So when people did this, they found that this worked. Now, the model wasn't trained to answer country capitals, but it was fed a lot of text. And that text included information where there were sentences involving the capital of France. And so there probably is many, many times in the text where it saw the capital of France is Paris. So when you ask it to autocomplete, it says the most likely thing to complete with is Paris. Great. So this is a very basic example. And this very basic example made people realize that. So this basic example is called an example of zero-shot learning. So what is zero-shot learning? Zero-shot learning is it comes as a modification of the idea of few-shot learning. And few-shot learning says, can you learn from only a few examples? And then the limit of few is 0. Okay? So here, you're giving no additional training data. You just have a problem. You just ask the model, you construct an appropriate sentence such that the autocomplete gives you the answer. Is that clear? What's going on? Okay. So notice this is different than everything else we've talked about so far. I want people to understand the difference. This is actually different. So then, this thing gets called a prompt. Because it's called you prompt the model by giving it some input, and you see what it says. But this prompt is actually from a prompt template. The capital of insert country here is okay? And so the idea with prompts is that you can also solve your task by coming up with the appropriate prompt template. Okay? And a mapping. So what you do is you make a map xi, and out pops prompt I. Prompt I then gets fed into a GPT-style model. What matters here is that this is something which takes sequences in and emits sequences out. So it's an autoregressive thing that generates. It doesn't matter that it does it autoregressively. This is important. Just that it's generative. Okay? Sequence to something. Model. And then what you do is you put another box that extracts what you want. So you treat the GPT model as a black box. There's no gradients of any kind here so far. In fact, everything here is human done. This is human engineered. So humans make this. Hand craft this box and this box. In particular, these are handcrafted boxes that run on a CPU, are programmed in human-readable programming languages when this whole process started. Okay. Everyone good with this? Great. So then people got to thinking, how well does this actually work, and what can we do with it? Okay, so this is sometimes referred to, the general area is referred to as prompt engineering. Like, how do you do this? I would say prompt engineering right now is somewhere between a pure craft, a human craft that people do from intuition, to something where they're beginning to become some principles and engineering approaches to it. Prompt engineering is an aspirational term. It isn't quite at engineering level yet, but it's aspiring that way. So you have this. So then what do you do? How can you go beyond this? So people saw that this only kind of worked. The fact that it worked at all was great, but not really reliable to work well. So where do you go from here? Everyone understand so I think this might be familiar to people, but I want to make sure everyone's on the same page. So then what people said is, can I do few-shot learning? And so for few-shot learning, you have some examples. For the task. So how can you use this training data for the task? Well, one approach in the prompt engineering style is to say, embed it into the prompt idea. Embed training data into the prompt. So the example of this is change your prompt. Instead of just saying the capital France is and asking it to complete, is you say new prompt. Let's play capitals. For example, the capital of California is Sacramento. And you keep doing this. Okay, so that it fits in your context length. And then you say, the capital of France is, and then you let it complete. So what you do is you give it context. And the idea of the context here, in this kind of few-shot use of prompt engineering, is to embed the examples into the context to help direct the generative model to the right answer. Is this clear as an approach? Great. So people did this, and this worked better than just the handcrafted prompt that didn't have any examples at all. But the few-shot learning performance of this kind of handcrafted prompts wasn't great. And so there's two issues. One issue is, what would you do if you actually had more training data than would fit into the prompt? Does everyone see that? Right, there's like a challenge here. If you have more training data than will fit in the prompt, because the context length is some length, and you can't fit all your training data in that constant context length, then what do you do? So does anyone have an idea for what you might do? Again, just using your generic set of conceptual understanding that you have across machine learning. Yeah. Okay, so the question is, can you somehow chop it up and separate it? Yes. So what does this remind you of? Batches, but okay, but batches aren't quite right. Because remember, the challenge here is that this model, right now, we're treating it as a complete black box. All we're going to do is we can call it however we want, right? But we can't touch it itself. So if you say, so one approach could be you take your data and you batch it. So you take your training, your few-shot data, and you say, I'm going to take my few-shot data, and I'm going to suppose that I can only fit 1/20th of it into the context. Does everyone understand what I'm doing? You only fit 1/20th of it into the context. So what I'll do is I'll take my training data, my few-shot training data, and I'll split it into, I'll shuffle it into 20 batches, right? And then I'll ask the same question 20 times with 20 different sets of training data. Then what will you do after that? I get 20 answers. Now what? So you said a weight update, but I can't update any weights because I have a black box access to this. Right? I can't touch it, touch the inside of it right now. Okay, so I could try to say, then I take these 20 answers and I treat these as features. And then I train something on these features. Great. Alternatively, you could say this feels like a random forest. Right? This is a GPT-style forest, right? Where I just treat black box and I just do that. Which then says, okay, great. If you do it that way, right, batches approach, treat it like a forest, random forest, then you could say, hey, maybe what I can do is actually think of these examples, and I can leverage the thinking that I know from support vector machines, and to say there should be a duality between examples and features. And maybe there's actually a set of these that are the ones that are the best examples. So remember in SVMs that your decision boundary is determined only by the support vectors. So maybe there's something like a support vector here that can be found. And you can try to do all kinds of cool optimization approaches, try to pick, and have your prompt itself be trained in the sense of which training data, which gets embedded into it. Okay, so there's lots of such tricks that one can do. And they will make things work a little bit better. Everyone good with that so far? Okay. So this is, let's call this all basic level prompt engineering. But what all this basic level prompt engineering neglects is that you actually don't just have black box access to this thing. This is actually a neural net with weights and parameters in it. And so what I want to do next is to talk about, oh, I've got myself into a corner again. Okay, that's okay. What can I do? Let's push this over. Okay, everyone remember that picture? I'll redraw it here. Some of it here. So the idea I want to step back and say, the idea is, can I think of it the way I think about fine-tuning? Can I do some kind of gradient updates? Okay, because if I actually have this thing as a neural net, if I wanted to, I could push a gradient through it. And if I pushed a gradient through it, what would I do with that gradient? Okay? The problem, when you look at this, when you start off, you look at this, it feels at first glance like it might be hopeless, because the prompt is a string in a discrete language. The extractor is parsing something from this language to give you something out. So it feels like even if you had a loss function on this, right, it's hard to think about getting a gradient back to the prompt. Do you see that? Because the prompt is the wrong kind of thing. And this is also a little bit annoying. Okay, but actually, we know we can solve that problem, right? So let's come back to it. So what's the question? Can I get prompts by gradient descent? So here, we have to go back and think about the transformer architecture. We have a tokenizer. Then we have a token embedding. And then I have a transformer stack. Okay, so this is like layer after layer after layer of attention, blah, 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 right? So the prompt is a string here, an English string. It goes to a tokenizer, it goes to the embedder. So suppose, for simplicity right now, suppose that what we have is we're going to use a transformer, run the entire prompt, and then we're going to look for a one token answer. Okay? Suppose that we've embedded it so that our answer is going to be one token. For simplicity, let's think about this case. A one token answer. If my answer is one token, then I ask this thing to generate something. So it gives me a bunch of probabilities of generating the next token, right? Suppose I could put a loss function on that for my task. So I have task-specific data, so I can have a task-specific loss. For example, I can put a cross-entropy loss if it's a classification type thing. Everyone with me so far? So suppose I did that. And now I tried to do SGD. Okay? Let's just watch the gradients go. Okay? So I start with some prompt, some English text. Okay? So gradient goes happily, 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 right? And then stop. Right? Does everyone see that? It goes happily down to the embedder, right? And then it stops. Now, what do I have right now? I have this prompt and I have this embedder, and the embedder is weight shared. Right? There's weight sharing here. Every single, remember? Everything in here is weight shared. So I use the same embedder all the way. So I have this gradient, it's going like this to all these weight shared copies of the embedder. Right? And I have a prompt, which is some sequence of text that I have, which is selecting specific tokens here. But I can't go back. Like, I can't get a gradient back to tokenizer because I can't say, can you make cow a little bit more in this direction? And the answer is, well, there's no word right next to cow in that direction. There's only cow, right? It's a discrete word. So gradients stop here. But this is where you have the key idea. The key idea is soft prompts. It says, who cares about this text anyway? All you care about is these real numbers. Yes. Soft prompting. Because you can do gradient descent onto these vectors. So one way of thinking about it is as follows. You say, these transformer-based models, or any of these machine learning models that run on GPUs, English or any discrete thing isn't their native language. What they actually like processing is vectors. So the insight is, why would you think that a prompt in English or in Tokenese would actually be the best prompt? The best prompt would be in their native language, because you're asking them to do something. So it would be in vectorese. And so soft prompting says, we don't speak vectorese, but gradient descent does, right? And so you get the prompt in vectorese. So it's just a sequence of vectors that don't correspond to any tokens. So the shocking thing was that when people tried soft prompting, they found that the performance increase was dramatic on tasks. That the performance increase kind of went almost all the way to full fine-tuning with just tuning the prompt. So again, we can think more back to what's going on with the transformers, right? You don't actually, so let's follow these gradients, right? Right? They're moving along, right? But actually, on these gradients, there's entries that are, think about all this that's happening, right? When this thing is actually generating something, all it can see back here is a bunch of key value pairs populating the tables. That's all it sees. Everyone understand that? Right? That's the transformer, the only thing the next thing sees is key value pairs from before. So who says those key value pairs actually have to correspond to the transformer outputs for any actual prompt? You see that? You can actually have soft prompts all the way up. Just take the key value pairs at different levels. And the gradient's gonna, this gradient comes back, it's gonna go through here, right? And then it'll keep going. But say, fine, I'll just change you. You see that? It's kind of an interesting idea, right? Because this requires understanding how things are built. So once you realize that you can change these key value pairs directly, you can also have soft prompts that are at different levels of the stack, of the transformer stack. So what people found was that by doing soft prompts of this type, first, the number of parameters that you have to store is very small, right, relative to the entire, all the weights in the transformer. There's lots and lots of weights in the transformer. In particular, just think about just the weights in the embedder itself, right? So soft prompts, even soft prompts all the way up, are very cheap in terms of memory as compared to the entire model. Yeah?
Is there still a GPT model, or is the full transformer GPT?
Oh, this whole thing is GPT, right? GPT, the GPT model is a transformer that run sequentially, right? It's trained on next token prediction, but the weights are associated with one stack. Its weights, because they're weight shared across different time sequences, time points, right? So what we're doing here is we're running GPT forward. We start with an English prompt or a random prompt, and then we say, great, now just tune on that loss. Make that prompt be better for that loss. And then, seeing that we can then learn it and train it. So it's a kind of a different style of fine-tuning that's between full fine-tuning and classic, except it's kind of all on a different axis. And it says that when you have a model that takes some kind of input naturally, you can also train the input for your task. And so there's like many papers on soft prompting and many variations you can do to improve performance. But the important thing is that the performance from soft prompting can often approach that of fine-tuning. And people saw a very interesting fact, which is that as the underlying GPT-style models get bigger and bigger, the power of soft prompting gets closer and closer to full fine-tuning. In small models, it's good, but in very large models, it's great. So there's many interesting things about this, actually, which is, so first let's pause here. Any questions on the idea of soft prompting? Yeah?
How do you use it? Like, actually, what do you cut the soft prompting with a real question, for example, in this scenario?
Yeah, so for example, one way you can use it, let's go back to over here, is you say, take your training data. So everything that would go here, let's play capitals, for example, blah, 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 blah. All this is replaced with vectories, soft prompt. So is the capital of, right? But then here, you use the embedding. Now you use a straight embedding of the question you want to ask. Comes in. The modification of this, the further modification is you add a small MLP that translates this embedding to something which is even better. You see that because the embedder, you do modification of the output of the embedder with an MLP that changes this. That only works if the set of tokens that are going to be queried are reasonably small and you've seen in your training data. Otherwise, how could you possibly have to update them? Okay? But that's how you use it. Yeah?
Does doing things like asking for the model to repeat things get you to have this embedding closer to English or something? It's sort of like a reconstruction.
Okay. Yeah, it's a great question. So let me acknowledge your question first, and then I won't be able to fully answer it. So the question was, given that soft prompting exists, can we use this for understanding interpretability? I'm going to translate your question, okay? To say, can we understand what these soft prompts are sort of saying? Did I get the spirit of your question? Yeah. And so one way of trying to do that is to see if you ask the model, say, let's play repetitions. I will say let's say something again, right? Let's paraphrase it so that a 5-year-old can understand. Say something. So imagine playing that task. And you say, great, play that game. Now, inject soft prompt here. What the heck is what does that mean to a 5-year-old, right? That's the style you're saying, right? Yeah, very interesting. I've not seen the papers that do this. I'm sure people have tried, okay? But I wanted to acknowledge a precursor to your question, okay? The precursor to your question is this thing. Remember we said there's a weird thing about this thing learning, about word-to-vec kind of knowing analogies, even though he wasn't trained to do analogies. So people said that GPT models, the fact that they can do this zero-shot learning is a kind of autocomplete. It's a very interesting autocomplete thing that they do, but it seems like they actually have some world knowledge that's built in that they had to learn. When you were doing few-shot learning, it's felt like it's able to generalized, which is also, it knows that that's that thing. When people thought about fine-tuning, full fine-tuning, it felt like, okay, great, we're actually, full fine-tuning, we're learning new weights, we're actually injecting task-specific knowledge. The fact that you can achieve almost the same performance by just soft prompting, just tuning the prompt in a soft way, made people step back and wonder, wait, does that mean the GPT model had already actually knew how to do that task? Or it already had that capability built in? It only required to be asked in the polite way to actually do it, or to give it instructions, short instructions on how to do it. So that kind of led to this question of like, what really are these things doing? Which is still open. Like, people don't know. So yeah, so that then leads to the question of using them to reflect on themselves, right? Which is the spirit of your question. Okay, I'm out of time. I will stop here. I wanted to get to meta learning, but I will do that next time.